And now you have to discover a chemical compound that will attach to the right place on the protein, right? And you want to know how strong will it attach, and then on top of that, even more important is not just will it attach to the thing you're interested in, make sure it doesn't attach to other things, because if it does, that will be toxicity. So you don't want it to have these side effects, or we call it side effects with drugs. So you want to minimize those. But because now we have all of these amazing algorithmic tools, we can sort of do a virtual screen of like, oh, here's a compound one of our AI systems has designed. It binds, this is our prediction of how strong it binds to the protein surface. And then we can check that very quickly, like in a matter of hours, that particular compound, how does it attach to any of the other 20,000 proteins in the human body? And so we can just do it like that, within a few minutes, and then keep modifying the compound so that it has less and less side effects, ideally none on any of the other proteins, but increasingly strong effect on the one that you want. So you can see I've just outlined a self-improvement process or self-modification process, and this is extremely fast and efficient if you can do it in silico, and then on computers, and then at the last stage, only at the final stage do you check it in the wet lab. So you still have to validate it. You can't. You make all these predictions, you do all your search in silicon, but then at the final stage you check your final proposed compounds in the wet lab, and then check it really does what the predictions say. But that, you can imagine, would save, you can search thousands of times more compounds, or maybe even millions at some point, more quickly and efficiently that way, and then just at the end check that they're correct. That's so much more efficient than doing the search in the wet lab, which is what effectively is done today.